Okay, we are live. Great.
Heather?
Yeah, I'm here.
Hello.
Yeah, it's, let me, to visitor, just so it's faster. It's just a little bit laggy, just like a tad bit.
Oh, gotcha.
This won't kick me off. I'm gonna try to switch my internet real quick, because I'm sure it's me. Everybody in their dog is on.
Okay.
There we go. Okay, cool.
Okay, cool.
Okay, see the questions there. I have the answers here, and then what?
Okay. Do you want to go first?
Yeah, sure. I can go first. Are you ready, Heather?
Yep.
All right, cool.
Okay.
So the first question that we had for our group problems was talking about genetic disease with an autosomal recessive. It's inherited in an autosomal recessive trait, in an autosomal recessive fashion. And so the data that it gives us is it says that this disease, 1 in every 150,000 people. And so what I did is I said, okay, well, that's got to be our recessive squared disease or allele. And so I did the math for that, and 1 in 150,000 is this number right here, 6.6 times 10 to the negative 6. And so then I took the square root of that number, and I got this number here. And then took 1 and subtracted this number, and then I got the dominant allele, and I square rooted that and got the the dominant squared allele. And from there, I could be able to calculate everything else out. The frequency of the small d allele, the frequency of the big D allele, the frequency of the big D allele, and the frequency of the both of them together, the heterozygous right there. And so right here, you get everything that you need by just using the Hardy-Weinberg equation. P squared plus 2pq is equal to q squared, or equal to 1. So using that, I was to get the answers to the first one.
Okay, for the second one, it was just fill in the blanks. For part A, it says determine Hardy-Weinberg equation that represents the IB allele would be the Q, and then the one that represents the IA-IB would be the 2PQ. For part D, it says that 1 in 4,000 individuals in the population are affected by a DiGeorge syndrome, and it asks what is represented by the Hardy-Weinberg equation, and it should be the P squared and 2PQ. And for part C, the question goes off of part B, and it says 3,999 and 400 individuals is the population unaffected by this syndrome is represented by what term? And that should be the Q squared term. And then in part D, it talks about different plumage found on mallard ducks, and MR is more dominant than M, which is more dominant than little md. It asks what term in the Hardy-Weinberg equation is going to represent the MD allele, and that should be the R term. In part E, it also asks about the Hardy-Weinberg equation relating to part D, representing the genotype of a duck with restricted plumage, and that should be the P squared or 2PR. In F, it asks what disease is a result of SNP, and it should be sickle cell anemia. G describes a trait that produces a single phenotype. 99% or more of the population should be monomorphism. In part H, what's in our local population should be DEEM. Is that how you say it? DEEM?
Yeah, I think so.
And then what genes in human morphic should be the MHC or major.
Oh, sorry, it froze. I can't tell if you're done.
Oh yeah,
Oh.
we're good.
Okay,
Yeah.
great. So for number 3, it talks about the Marfan syndrome. And so it says that it's an autosomal dominant disorder, and it affects 1 in 6,000 individuals. So the first question asks what the frequency is of the non-disease allele in the human population. And you figure that out by doing the square root of Q and the square root of 5,999 over 6,000, which equals this number here times 100, which is 99.9916%. For part B, it asks what is the frequency of the Marfan syndrome allele in the human population. And so for that one, you do 1 minus the number that we calculated up here. So that is this number here times 100 is 0.0083% or 8.33 times 10 to the negative third percent. For part C, it asks what is the frequency of the heterozygous individuals in the population. So for that, you use the 2pq part of the Hardy-Weinberg equation, and you do 2 times the p-value times the q-value equals 1.6673 times 10 to the negative 2%. And for part D, out of a population of 5,000 people, how many heterozygotes are expected? And for that, you take the number for what we calculated up here, which was heterozygotes, multiply that by 5 million, and that equals 833 people.
Cool. So for that was question number 3. So for question number 4, it's asking about some different kinds of alleles, or sorry, a few different types of genotypes. And it gives us the number observed from these genotypes and asks us to find the allele frequencies, and from that to come up with a chi-square test. So from there, what I did first is, I'll just fold it here so it's easier to see. First thing I did is I tried to figure out what the allele frequencies were here. And so for R squared, I took the value of R squared, well, the heterozygous here, and the heterozygous genotype plus the homozygous R squared genotype, and times that by 2, divided by the total times 2, and you end up getting the allele frequency, and then you just do the same thing for the R cubed, and you get that allele frequency. And so by knowing these allele frequencies, you're then able to come up with the frequencies of each of these genotypes right here. And then from knowing the genotypes and their frequencies, you can go ahead and make a chi-squared test. And so I took them here, the different kinds of genotypes, the observed right here, I hope you guys can see that, observed right here, the expected here, and then the equation here, and that's what I got there. I added them together, and I ended up getting 7.182. And so that ends up showing that what is observed and what is expected is not in equilibrium. And my suggestion as to why is that perhaps there is some kind of natural selection happening, and it is causing the R2 or R squared allele to become to allow evolution to occur, because it increases the fitness of the organisms with that allele.
Okay. In question 5, it talks about different coat colors that are controlled by the alleles in the population. And so I just wrote out which ones were dominant to the others. So chinchilla is going to be the most dominant, then the white dog with dark eyes, then pale gray dog, and then an albino dog. And then from there, for part A, it asks what's the frequency of chinchilla dog, and then a pale gray dog, albino, and then a completely albino genotype in the population. For here, you can see the calculations, and for the first one, I got 0.1369. For the second part, I got 0.075, and the third part, I got 0.0225. And then for part B, it asks, for 2,000 dogs, how many would you expect to have the pale gray phenotype, yet be heterozygous? And that would be 150 dogs. And then for part C, it says among the population of 5,000 dogs, how many would you expect to have a white coat with dark eyes, yet be heterozygous? And that's going to be 920. And then for part D, it says among a population of 15,000 dogs, how many would you expect to have a chinchilla or pale gray dog, or just a completely albino dog genotype? And you're going to get 3,112. And I think I got 3,113 because I probably rounded up, but that's 3,112 should be the right answer.
Mm-hmm.
Great. Cool. Well, thanks for watching.